Thank you. Thank you. Hi, I'm Noam Shazeer. I'm from Google AI, Google Brain. And I want to talk about neural language models and why you should be training bigger ones and how to train bigger ones. All right, so just to motivate this, I trained some transformer language models. This is identical to half of the model that we use for machine translation, just the decoder half. So just a autoregressive generative model of text, and used the text of Wikipedia to train it. And I seed it with the title Abraham Lincoln, which happened to be in the held out set. So it's not just repeating the article it read. So here is a random sample from a model with about 30 million parameters. It's mildly grammatical, looks, but semantically not very meaningful, looks like other garbage, doesn't know much of anything about the world. As we make the model bigger by just increasing the sizes of all the layers, it seems to make a lot more sense, though it bears no bearing on reality. Just pretty much made up everything. Insert your favorite political joke here. Make the model even bigger, 300 million parameters. Kind of remembers that Abraham Lincoln was a 19th century American politician. Looks a lot more realistic. Go up to 1 billion parameters. And it got his date of, his year of birth right, and remember he's an orator. And by the way, all of these are word piece-based models, so there's no out-of-vocabulary. And then this one actually was trained for a bit longer, but 5 billion parameters, trained for a couple days on the TPU pod, the 500 cores, 11 petaflops, and it actually looks pretty good. About half of this is true, and the other half is mostly made up. But okay, so I mean, it stands to reason that if you want to know a lot of facts about the world and to generate language, you need to know a lot about the world, and you cannot remember a lot about the world if you don't have many parameters in your model. There's 7 billion people in the world. If you want to know at least one thing about every person, you better have at least 7 billion parameters, and we haven't even gotten there yet. So if big models are better, why do people train small models? And the main reasons, as I see it, are generalization, speed, and memory. Like, you don't want to overfit your tiny data set, so you train a small model. You want to train it fast. And you only have so much memory on your computer, so you train a small model. So my message is, if you are training small models, then something is wrong with you. But that's okay, because we'll try to fix those things so you can train big models instead. If your training set is small, there's no real reason for that. Or maybe your computer is slow, and for memory, we've just written a new language called Mesh TensorFlow, which is going to help people distribute their models over many processors. Okay, so first, if your training set is too small, there's plenty of bigger training sets out there. Download the Common Crawl or something. You can get trillions of words of unlabeled text to train a generative model. And you can actually use generative models to solve a lot of problems based on the recent work from OpenAI. At least it's very useful to train a giant, or any size, generative model. You can use it for a lot of things, and probably the bigger the better. Okay, so on to your computer is too slow. One reason, well, training a model, the cost tends to be quadratic in the number of parameters because, okay, now you have more parameters, it's more work to process each training example, and you want to process more training examples to fill up your brain because your brain is bigger. So say we want to train a 1 billion parameter model on 1 billion words of training data. That turns out to be, it should take you roughly a day on 100 teraflops machine, which you should be able to rent off-peak from Google for about $1 an hour. So that we're trying to make that accessible to everyone relatively cheaply. But if we want to, I mean, and 1 billion parameters is already bigger than most people use for most anything. Most of the models people are using are on the order of 100 million parameters. But we'd really like to blow things out and do like 100 billion parameters. And there we might need like a 100 petaflops machine for a week or something. So of course we're building supercomputers at Google, which we're going to use for this purpose, hopefully. We call them TPU pods, and we're doing our best to make them available on cloud so other people can use them as well. Another way to deal with the computational costs is using sparsity. The easy way to do this is just big embedding layers over some big vocabulary or something, but that's kind of lame. Another project I was working on involved, we called the sparsely gated mixtures of experts, where you have an internal layer of the model which has a huge number of parameters, but a limited amount of computation per example, because the layer is made up of a bunch of feed-forward networks, which we call experts, and then you train a gating network that for each example, maybe for each word, is sending the input to only a very small subset of, say, 2 out of 1,000 of these experts. And since the experts themselves are each dense networks, you can actually run this thing at the speed of matrix multiplication on GPUs or TPUs. And this should give you a way to speed up your computation by like a factor of 100, 1,000 or something, and train much, much bigger models with limited computational costs. So maybe we'll be able to train a 1 trillion parameter model on like 1 trillion words of training data, but maybe only do like 1 billion computations for each word. That could be a talk in itself, but we'll move on. So the thing I really want to talk about is the memory problems, which is that your processor might not have enough memory for a giant model, and so you really need to split the model across many processors. And you call that model parallelism, as opposed to what people usually do, which is data parallelism, which is you have a lot of processors and you put the entire model on every processor. And model parallelism can be very tricky to implement. The usual way to do this is to assign different tensor operations and different tensors to different processors, and you have to come up with a new scheme for every model you build. It's tricky to design an efficient algorithm because you might have imbalance, you might have a lot of latency in the network, a lot of bandwidth in the network, and it generally will create a giant graph that'll take forever to compile. So people don't generally do this because it's highly irritating. Instead, what people do is called data parallelism, which is you put the entire model on every processor, and then you just send different mini batches to the different processors. We do this all the time on our TPU pods, and the batch is split among the different cores, and then you run the forward pass, you run the backwards pass, and then you just need to add up the parameter gradients across all of the cores, which is an operation called all reduce or cross-replica sum in TensorFlow. It actually, there are super efficient algorithms for this on locally connected networks, and so it runs really fast. And things are great as long as your whole model fits on one core, which it won't. So, I mean, the great things about the data parallelism we use is it'll work on any model. It's fast to compile because you're actually only compiling a program to run on one core, and then you just distribute that program everywhere, and the communication is by these collective communication primitives, MPI style. You can get full utilization if you can, if your cluster is full of homogeneous, same identical processors, and the communication tends to be fast. And the problem is it's not going to work for large models because you have to fit everything on every processor. So instead, we've invented a language we call Mesh TensorFlow, thanks to a lot of people at Google who have been working on this, and we have it out in open source. It's part of the tensor-to-tensor library. So the idea here in Mesh TensorFlow is to take what works well with data parallelism and to use that for model parallelism. So again, every operation is going to be split across every core. Every tensor is also split across every core or replicated across every core, or some combination of split and replicated, which I'll explain. Every core is running the same program. It's the same SIMD style of programming, and we use collective communication primitives sort of on the back end to implement all of this stuff. So the way Mesh TensorFlow works is you write your graph in Mesh TensorFlow, which is almost identical to TensorFlow, except you name your dimensions. And then instead of always splitting the batch dimensions, you can specify which dimensions get split. So if you're doing data parallelism, you say, I want to split the batch dimension across all of my processors. And if you want to implement some kind of model parallel scheme, then you specify the names of some of the layer dimensions, and those instead get split. So as an example, let's take just a three-layer fully connected network with an input layer, a hidden layer, and an output layer. So the data parallel way to do this is to say we're going to split the batch. So any tensor that has a batch dimension marked B gets split across all the processors, and any tensor that does not have a batch dimension, meaning the parameter matrices W and V, is replicated identically on every processor. And so the forward pass, actually, there's no communication, but in the backward pass, it turns out that you need an all reduce when you're computing the parameter gradients. And that's going to happen whenever you are doing a matrix multiplication and reducing out a dimension that's split. So instead, we want to do model parallelism, and now we're going to say we're not going to split the B dimension, the batch. We're going to split this hidden dimension, D sub H. So what that essentially does is it means that the weight matrices are now split across that hidden dimension, as well as the activations of the hidden layer. And then when you're doing that second matrix multiply in the forward pass, you're reducing out a split dimension. So on the back end, Mesh TensorFlow is going to perform an all reduce operation to get to compute the right results on all the processors. Instead, you could be deciding to split the D sub X and D sub Y dimensions, and then you get some different model parallel algorithm. Or you could do something really crazy, and now we're going to split roughly all of the dimensions, but we'll assume we have a three-dimensional mesh of processors. We're going to split the batch dimension across one dimension of our supercomputer. We're going to split the hidden dimension across the second dimension, and we're going to split the input and output dimensions across the third dimension of our supercomputer. And now all of these tensors are tiled and replicated in different ways, and you get these all-reduce operations all over the place, but the thing actually does run and gets distributed in this interesting way. This also works for actual networks we want to run, like Transformer. That's how I ran those experiments I showed at the beginning of the talk. So for Transformer, doing model parallelism, you split the vocabulary dimension, the number of attention heads dimension, and we have a feed-forward hidden dimension, and all of those get split across the same dimension of the processor mesh. And that works out because roughly every large matrix multiply has exactly one of those dimensions in it. And then we can, and on our 2D processor meshes, we split the model in that way across one dimension of the mesh, and we split the batch across the second dimension of the mesh. So we are actually doing data parallelism and model parallelism with each row of processors handling a part of the batch and each column of processors handling part of the model. So that works out really well. We were able to train these transformer models at more than 50% efficiency over our giant 11 petaflops supercomputers, 512 cores. And so all of this is awesome. And so the basics of the language is it's a lot like TensorFlow, Python API, and it compiles down to TensorFlow. You just have to specify dimension names for all your tensor dimensions, and you specify a layout of how those tensor dimensions map to the dimensions of the computational mesh. And all of this is available as open source now, and it should work by now on our cloud TPU. Of course, it's not that simple. You still need to know which dimensions of what to split how and to know the performance implications of all of that. It's not like just open the box and anybody who doesn't know what they're doing can use this. But if you do know what you're doing, it makes it a lot easier to devise and specify these model parallel algorithms than if you didn't have mesh TensorFlow. Okay, so then, so the status is that the code is out there and under development, and we'll be publishing a paper soon and getting it out on archive. Any questions? Yes?
So I guess for data parallelism, during inference time, you just need one GPU most likely. But for
right.
your case, I guess, even during inference time, you still need multiple devices.
Right. You can do inference without model parallelism if your model will fit on one device. But yeah, if you create a giant model that doesn't fit on one device, then you want to split it at inference time as well. And that's actually wonderful because it means that inference can be a lot faster, because now one example during inference is actually split across the compute and memory bandwidth of multiple devices. So I've actually decoded like 1.5 billion parameter transformer translation model in like a couple milliseconds per token by splitting it across like 8 TPU cores, and even better, splitting it across 32 TPU cores. Yes?
So I got a question. So why the shared memory programming model doesn't work here? So in that case, in supercomputers, so you mentioned about memory pressure. So you have shared programming model, so you can just shift this kind of programming burden to the system layer. And I believe there's the established works in supercomputing community, right? So why?
Oh, okay, yeah, this is very similar to a lot of the work in the supercomputing community on, how do you distribute linear algebra operations like matrix multiplies. So this builds on a lot of that. The sort of major novelty here is that instead of talking about one linear algebra operation, you're talking about an entire computational graph. Okay. So what makes sense for one operation may not make sense for an entire computational graph. In particular, you want the output of one operation to be laid out in distributed memory in the same way that the next operation wants to use it. Right. So by specifying for the tensors how they're laid out, then you're going to be using the same layout for the output of one operation and the input of the next operation, because really what tends to be expensive is moving data around. So you're on the supercomputer where each each processor has its own local memory, so you have to be very conscious of what data is living on what processor,
Okay.
and making sure the layouts are right.
Okay, so the problem is, I think the data movement is really expensive here. Okay, thank
Right.
you.
Yes. Thank you. Okay. Thank you.